All right, so today we're going to do a lot of in-class practice, but I'm going to do a warm-up problem first to describe that 1,3 diaxial interaction that I was talking to you about. All right, so yesterday we did cis 1,2 dimethyl cyclohexane. Today we're going to do a warm-up that's similar. All right, this time I'm going to give you the 2D bond line structure. I want you to draw both chair conformations that represent this 2D bond line structure, and then from that determine which one's more stable. So I'll give you a minute to work on it, but like I said, 2 different chair flips. All right, just for the sake of time, let's try to do this as a class. So what I did for my bond line structure was I numbered it, and I numbered going clockwise, and I just arbitrarily numbered it. In this case, I could have numbered position 1 where position 3 is. It doesn't really matter. All right, so I numbered going clockwise, and then in my chair, I also numbered going clockwise. It's important to keep things consistent. All right, so position 1 in my chair structure, I should have an axial substituent sticking straight up and down like that, and I should have an equatorial substituent that is parallel to the bond line between 5 and 6, right? All right, where's the methyl group going to be? Is it going to be sticking straight up and down in axial, or will it be equatorial? Axial, okay. Again, if we have the little man on top of this looking straight down, the methyl group would be closer to our eye than this hydrogen, which makes sense. All right, let's skip carbon 2 because we don't really have anything coming off of there. We'll jump to carbon 3. Same idea. We should have an axial substituent and an equatorial substituent. Where will the methyl group be? Axial. All right, and then a hydrogen over here. Looks good to me. Let's go all the way over to 5. Again, we should have an axial substituent and an equatorial substituent. Where will the methyl group be? Axial. All right, so it looks like we've got our first chair taken care of. Like I said yesterday, I always imagine this bond, or sorry, not that bond, that carbon to be my headrest on the left, this one my footrest, and we've got these kind of imaginary hinges. So I'm going to pull this footrest up. I'll pull that headrest down. Then we'll go over here. Now, if you kept track of our footrest, that was carbon 2. It should now be sticking up. So I'll go ahead and label this 2. And then we'll go down here as 3, 4, 5, 6, and then wrap around to 1 now. All right. So the hinges were always between carbon 6 and 4 and 1 and 3, but now our footrest is our headrest and our headrest is our footrest. All right, so now carbon 1. Let's zoom in and look at this. Carbon 1, we should have an axial substituent, and in this case, the axial substituent is going to be sticking down, like that, and then an equatorial substituent sticking out and away. Where will the methyl group be now? Equatorial. And then this axial substituent is going to be a hydrogen. All right, and then position 3, we should have an axial substituent sticking straight down, equatorial sticking out and away. Where will the methyl group be? Equatorial. Hydrogen will be axial. Then we'll go over to position 5. Axial is down, equatorial is out and away. Where will the methyl group be? Equatorial. All of them went from axial to all equatorial. All right, so let's try to imagine this with our model kit. I've got one model kit here. You see how all the methyl groups are axial. And then I grab opposite side carbons. So grab the top half and bottom half. I'll flip one down, the other one up, and now they're all equatorial. Which one do you think is more stable? The one where it's all equatorial. Yep. So let's go ahead and circle this one. This one's more stable. And if you noticed, I used equilibrium arrows. You can actually measure this equilibrium, determine how much of each you have in solution. And the reality is you're probably going to be like 99.9% this conformer, maybe 0.1% the other conformer. So in equilibrium, it can flip-flop, but it really doesn't want to very much. It's a really lopsided equilibrium. This is referred to as a 1,3 diaxial interaction. And I'll show you why really quick. Sorry. This is carbon 1. This is carbon 3. There's two axial positions on carbon 1 and carbon 3 that are kind of bumping into one another in space. So this whole interaction right here is called a 1,3 diaxial interaction. This is really destabilizing for molecule, especially as those groups get bigger and bigger and bigger. In general, like I was saying, large groups want to be equatorial, not axial. Yep?
Are there any molecules where the axial position is preferred?
Not for a large group. So the question was, is there any chair conformation where axial substituents are preferred over equatorial? In general, your chair will contort itself to find the lowest possible energy conformation. There are weird examples where, trying to think of a good way of describing it, where there's no clear winner. Maybe in one structure you have just as many 1,3 diaxial interactions as the other. Both are destabilizing, in which case it actually won't stay as a chair. Rather than being a chair, it will twist into this almost figure 8 shape called a twist structure in order to minimize interactions. But that's more the exception than the norm. Does that make sense? All right. Yeah?
Since they were all, in the bond line, they were all coming towards us, is that the reason why they're all the same? Like they're all axial at one time and they're all...
Yeah, so the question was, if we think about the bond line structure versus our chair structure, I'm going to erase this and draw my super artistic little man again. If you think about it, right, all of these methyl groups in that chair structure are coming closer to our eye. Therefore, they're all wedges. In the other structure, do the same thing and say, all right, my little man's looking down on this. All the methyl groups on those carbons are still closer to our eye than the hydrogens that are attached. So therefore, they're all represented as wedges, regardless of the chair conformation that we're looking at. That's one problem with 2D bond line conformation for cyclohexane, is it doesn't tell you which chair conformation we're really looking at, nor does it let you know which one's more stable. Sometimes drawing a chair is your best bet. Does that make sense?